Recording. Okay, great. Cool. All right. Hope you guys had a great Tuesday. Homework 1 was due, and you should have submitted it yesterday at 11:59 p.m. So I did also ask, if you guys noticed at the very bottom of the homework, there was like a Google form you can fill out. It's not graded, but it was asking for feedback on the homework. Basically, like, how much time did you spend on it? Like, how hard was it? Because again, I'm still trying to understand and like get used to like where everybody is in the class. So if it was too hard or too easy, that's probably the fastest way to give me the feedback, and it also aggregates it across all the students. Homework 2 is going to come out today. It's actually already on the website. There's a few things I need to fix on it, but I'm looking at the feedback from homework 1 for the people that have filled out that Google form to try to like adjust the homework 2. So in particular, I did get a few students mention essentially there's some confusion on the homework as to like how to submit, like which parts are written, which parts are coding, etc. And originally my goal was to have you guys kind of like within a single problem, I would ask you conceptual questions to kind of help you come up with the algorithm. And then I would ask you to code it. And then we would go to like another problem and kind of do the same thing. So it was mixed. So that's what homework 1 was supposed to be like. For homework 2, given that there was like a lot of confusion, or not a lot, I think just like 2 or 3, maybe 4 students like showed some confusion there. And I agree, it was a little bit confusing. So based on the feedback, what I've done for homework 2 is the whole first section is just written. So it's just, you can from question 1 down to question 5, I believe, all of this, you're expected to like write it on a piece of paper and like submit as a PDF, or like, you know, another thing you can do that I would recommend is like, this is the easiest thing to do. You don't, you can do a Google Doc and you can just do, 1.1, and then you can write your answer here, right? Type your answer, and then once you're done, you can download that as a PDF and upload it to Gradescope. Okay. Right. So I am trying to make it a little bit easier for folks to submit that. So for homework 2, all the way from 1 to 5 is just written. Okay. There's no coding you have to do for those parts, and then the coding is actually just exercise 6, which is worth, I guess, 50 points of the homework. And this is just the same as you did for homework 1. There's a replet with starter code. You're going to copy it. And then what I did is, instead of writing the instructions in the PDF, they're in the readme.md in the replet. So basically the 2 parts of the homework, the written one and the homework and the coding one, are like kind of separate, just to make it a little bit easier for folks. And so there's no confusion as to like, is this part supposed to be coded, or am I supposed to like submit a written thing? Does that help? So that was a little bit of feedback. So again, I encourage you guys to give feedback. Every homework I assign you will always have a link to a Google form where it's going to ask you, how long did this take? How hard was it? Did you learn something new? Do you have any feedback? So I am trying to like adjust as you guys sort of like join, or like, so help me out. So definitely there's that. I do also know we had some issue there. Like, I think the homework 1 PDF was offline for a few hours yesterday. So like it wasn't on the course website. Did anyone have issues with that? Like, one?
You went to the prompt rating 5, like you're on that, it didn't show up. Like you went to the Facebook.
Yeah.
DIR one.
Yeah. So that was like a temporary thing. I am considering, like, I'm thinking of like offering like an extra day for homework 1. So it won't affect homework 2. That's still going to be released and due at the same time. But it would be like a 1-day extension because of those issues. I don't know how, I mean, the other thing is like, even if you submit late, you only lose 10% of the grade. So like, it's not like, but I don't know, like, how do you guys think? Like, I can do like a free 1-day extension till tomorrow, or actually it wouldn't be tomorrow. It would be like today, midnight. Okay, but it's not going to affect the due date for the next homework. All right, so just keep that in mind. Okay, so we'll do that. Again, also, let's just go ahead and get started. We're going to cover some pretty cool stuff today. But yeah, a couple of homework tips. I do encourage you guys to start early on the homework, especially the coding portions, okay? Because as a software engineer, I can tell you that coding is one of those jobs that you don't like, you will run into problems you didn't even know like existed. Okay, so if you're like, oh, this is gonna take me an hour, I'll wait till the last hour. It definitely won't. And a lot of the times the problems you run into are not like complicated. They're just like simple little things. So I would encourage you to try to get started early. If you run into a problem and you can't figure out within 10 minutes, post on Piazza or email me. So like the earlier you get it, I can unblock you, right? And that's actually how, like I told you guys, when I do my job, basically I hate waiting until the last minute because I will run into issues and it's a lot faster to ask for help than to get super stressed at the last minute because the homework is due. So I would recommend that. So definitely get started early. So again, homework 2 is going to be out. Like it's already on the website. Maybe take a look at it later today because I need to fix one thing in the coding part. But yeah, get started early. If you run into issues like things aren't compiling, there's a function you don't understand, like post on Piazza. If you post, like I try to reply pretty quickly. If you post tomorrow, you'll have your answer and then you can work on it again, you know, like on Friday. And then if you run into another issue, you can post on, you know, Saturday, I'll answer it. You can work on it on Sunday, right? Instead of waiting to the last minute. Cool. Does that make sense to everyone? Yeah, so I would just definitely encourage that. All right, yeah, so like I said, it's gonna be released today at 5 p.m. It's gonna be due next Tuesday. And yeah, welcome to class. How's everybody doing? Pretty good, pretty excited. Okay, me too, me too. So today we're actually gonna cover the substitution method. So it's gonna be, again, more math. Towards the end of the lecture, we are going to transition back towards coding. So we're going to get introduced to a brand new algorithm that is going to leverage some of the stuff that we've learned in the class so far. Okay. Yeah, so that's the big topics. We're going to do an advanced method for solving recurrence relations. So this is, again, like I am really trying to get you guys to be like the top of the top in like CS. So this is a little bit more advanced, but it's actually not that difficult. I actually think it's easier than the previous methods, but it's not often taught. So just, it's not hard. It's just not used as much, let's say. And then we're going to cover the case select problem, which I'll explain in a second. So again, from last lecture, just a reminder for you guys, we learned about the master theorem, master method, master theorem, whatever you want to call it. They might change the name of that because I think that's a little unfortunate that that's what it's called. Like that, yeah, anyway. But basically, it's a way, so the master theorem gives you a way to go from a recurrence relation to a big O running time without you having to draw the tree and do all the summation, because we did that once, right? Now, this lecture, we're going to be introduced to something called the substitution method, which helps you solve recurrences that the master theorem cannot. Okay, so in practice, I have actually never used the substitution method. Well, okay, maybe once, but I've used the master method far more often. Okay, so just keep that in mind. It's another way to solve recurrence relations. And the reason we're learning is because the algorithm we're going to learn on Friday actually requires this method to solve the recurrence relation. It's more general than the master method. So this works. And if the master method works, the substitution method works. Yeah, basically it's 3 steps. So the first step is you guess at the answer. Okay, so this is why I mean, like this method is like, I think easier, but just not as common. So you guess at the answer. Step 2 is you try to prove that your guess is correct. So you do an inductive proof. So I think that's why this is considered more advanced, because it requires doing induction for the proof. Okay, but you guys have already seen induction come up a few times. And then step 3 is you profit, which basically means you publish your results, and we'll talk about that. So again, let's go back to like our good old friend. So if you guys remember, this is our recurrence relation for merge sort. It's also the recurrence relation for a lot of algorithms. It doesn't have to be merge sort. It's just any algorithm that splits the input into 2, takes linear time to put it back together, and then calls itself twice, right? Everybody sees where that's coming from. Master theorem immediately gives you an answer. If you look up the master theorem, you compare the A, B, and the D. It'll tell you this is the big O running time. And in your homework too, I will give you, I think, 4 or 5 of these recurrence relationships and be like, use the master theorem to tell me what the big O running time is. All right. But now in this case, we're actually going to use substitution to prove this. So again, the first step is you guess at the answer. So guessing the answer, this is the part that requires a lot of creativity. And like sometimes you just like are inspired by divine inspiration. For the assignment, for the homework, probably a friend of you tells you like what the answer could be. Here's an example at how you might guess at the answer for merge sort. So here's our initial recurrence relation. And basically what we do is we expand. So this t n divided by 2, we start working it out. Like if we were actually trying to solve it, we say, okay, well, t n divided by 2 is actually equal to 2 times t n divided by 4 plus n divided by 2. So we like plug it in, right? Like expand one step, right? And then from here to this line, we're just simplifying. So we're doing like 2 times 2 is 4. So we have 4 times t n divided by 4. And then 2 times n divided by 2 is n plus n is 2n. So that's just like math, just simplifying it down. And then maybe we repeat this again. We say like, okay, well, now I have this t n divided by 4, right? This is the reason we said recurrence relationships are like easy to write, but hard to answer, because this is how you would normally try to answer it, right? And every time you plug something new in, you get like another, like your function comes in again, right? So it gets long. Does that make sense to everyone what we're doing in these steps? We're essentially like, for t n divided by 2, I'm saying this is equal to this by the definition of the function, right? Cool. So you can imagine trying this out for a few steps. So for this recurrence relationship, we know the answer. So we could have just guessed n log n, because we know that's the answer. That's what master theorem says. But in general, if you don't know the answer and you're trying to use substitution, you might plug in, you might like expand it out a few steps to try to see like, is there a pattern? Can I get a sense of what the answer might look like? So essentially, after you plug these in, you might guess that the pattern is t of n is equal to, essentially here you see this, like it goes from 2 to 4 to 8. And then like every time we expand, it kind of doubles the number in front of the t. So it becomes 2 to the t. And then every time, we go from n divided by 2 to n divided by 4 to n divided by 8, it kind of halves one more time, right? So you might guess that the answer looks something like this based on the pattern that you wrote. And then what you do is that trees have a height log n, like we talked about that quite a bit. Or you say like, well, because for this method, we're kind of dividing by 2, dividing by 5, dividing by whatever, the height is log n. So at the very bottom, I'm going to plug in log n into this equation. And that actually gives you this, n log n plus 1.
What would compel you to plug in log n?
So it would be a guess. So again, this is where you like I said, this method is more advanced probably because this part is like a little like, if you are being asked to do it, like if I'm telling you, I'm just telling you what to do. But if you're being asked to do it on your own, like you said, how do I know to plug in log n? So the reason for this specific example is that you kind of notice that you're dividing the input by some percentage each time. So either by 2 or by 3 or by 4. So it kind of gets smaller. So your sense is that I can only divide it so much, right? And the height of that tree, or like how many times I can divide it, is going to be log n, whatever the base is. So that's why we plug in log n here. There are other cases where like maybe you're not dividing the input. You might see recurrence relationships where you're doing like n minus 2. So it's like the input gets smaller by 2. In which case, like you wouldn't plug in log n. I'd probably plug in n, because like how many? Yeah.
Like how do you know like log n? Like I would never think to plug in log n. It's just like the log n is the step smaller than n, right?
It is like the number of times you divide by 2, let's say. Yeah. So yeah. No, like definitely, like again, like this first method, like guessing the answer, this is one way to try to do it. Other ways is just see like, you just look at the problem and something comes to you. So that's why this method is like, I guess, more difficult, because you don't always, like there's not a like step-by-step way to get what your guess is. You're just like, based on everything I know, I've looked at so many recurrence relations that I think this is going to be linear. I think this is going to be n log n. I think this is going to be n squared, right? And that's where like, I guess a lot of expertise gets developed. And I would say the people that can look at these and kind of guess this sort of stuff probably like are very few in the world. But anyway, but that's step one. If you can get a guess, then step two is you try to prove that your guess is correct. Okay, because what at the end of the day, what you want to show is you want to show somebody that what you guess is actually the right answer. So the way you prove it is you use induction. Okay, so we're going to practice a little bit with induction for this specific example. So again, if you guys remember, induction has a base case, inductive hypothesis, inductive step, conclusion. All right. So in our case, our inductive, like this is our guess. We're saying that the closed form solution of this recurrence is going to be T of n equals n times log n plus 1 parentheses. How did we get that guess? The previous slide tried to give you a way to get it. How you get it when you're doing research, it's up to you. Like you throw whatever you can at the problem and try to figure. You write out examples and you try to guess what it looks like. So this is the inductive hypothesis. So this is actually what we're trying to prove, right? So the inductive hypothesis is what we're trying to prove. The next thing we do is we show that it is true for the base case, for a simple case. So this is like super trivial. We say like, okay, if I plug in 1 for n, then T of 1 is equal to 1. So they gave this as part of the recurrence relation, which is actually equal to 1 times log of 1 plus 1. So I'm essentially plugging in 1 for n here. And if you simplify that down, that's equal to 1. Like log of 1 is 0, plus 1 is 1, times 1 is 1, right? So the base case should be easy for most folks. Or like it's an easy example, but now we have proven it for one thing. Like now we have like a foundation where we're like, for this case, it works, right? This is the whole point of induction is you're like, you get a foundation and then you show that for one more step, it works. And that means it works for everything. Does that actually make sense to you guys? Like inductive proofs, like why they work? Like first you have to prove for at least one case, like one solid case. And then after that, you basically prove that it can work for one more, like if I take one more step, it also works. And logically, that means that it actually works for all the numbers. Because like if I proved it for 1 and I prove it works for one more step, then if it works for 1, it works for 2. If it works for 2, it works for 3. If it works for 3, it works for 4, right? So that's why it proves it like infinite for every number, right? So that's what we call the inductive step. So the inductive step, this is like the same for every inductive proof, right? So a lot of this is like the same. You do it the same way for any inductive proof. You say, I'm going to assume my hypothesis is true up to some value of k, right? So we're just saying like, this thing that I said here might not be true for all n, but I will assume it is true for some value of k, up to some value of k, like right before it. It's true for all those numbers. Now, why do we do that? Because like I said, we already proved it for 1. So you can imagine here we're saying like it's true for 1. Can I show it's true for 2, right? But we use the letter k because we want to say like generally speaking, it is true up to some point. And now I am going to prove it is true for one more step, right? So what does that mean? In our case, it means like, you know, suppose this is true for everything less than k, right? You assume that is like part of, you know, that is the case now. Then you prove the inductive hypothesis. So you say like, well, if it's true for everything less than k, now I want to show it is true for exactly k, right? And that's how you get for like, oh, it's true for k minus 1. Now I prove it's true for k, okay? So that's actually, you like write out the math. It's actually essentially one step of your thing, but you say like, okay, well, I want to prove like, what is t of k, right? By definition, t of any number is this. So I'm just going to plug k into that. So 2 times t of k divided by 2 plus k. That's like given to me. That was the definition of my function, right? Now, what I notice is that this k divided by 2, right? It is smaller than k, right? So by my inductive hypothesis, I can actually replace this with this answer, right? Because I am assuming that I already know that is true, right? So we do like one step where we say like, okay, t k divided by 2, it's actually, we assume it is equal to this. like by our inductive hypothesis. So in this example, it would be like, let's say I'm doing k equal to 2. I already proved t of 1, like I already know what that is, right? So that's why I can do this. And that's basically like the biggest thing about induction is like you have a smaller case, which you assumed was true, right? So now we simplify the math. So if you just work this out, right? So 2 times k divided by 2, that gives you k. Then you have 2 times log of k divided by 2 plus 1. You have a plus k. So you can actually factor out. So here you get a k and a k. You can factor out the k. You're left with the log k inside, and you get a plus 1 outside. So this is from here to here is you like working out the math, which means just like distribute out your values, right? So this 2 distributes to this k. This k distributes into this log k2 and this plus 1. And then you're left with a plus k on the outside. That then you can. So essentially what you're trying to do is you're trying to get this. So this we just plugged in. You're trying to get this to look something like this, right? So this is where like most of the work is in the actual proof, okay? But eventually you do get down to this by simplifying, which now it should be obvious, like, well, this is exactly what we wanted to prove. We wanted to prove that t of k is equal to k log k plus 1. Right. So this is where like the real work happens, I would say, going from this line to this line, but it's actually just math, like distributing out your variables. Everything else is kind of like a template that people use. And then the reason they call it an inductive proof is because like now that we've proven that this holds true, now we know it holds for every single value of n. So now we have actually shown that t of n is equal to this, right? So we didn't use the master theorem. We didn't use trees. We used induction, and we showed like the same thing we've seen a couple of times. All right. So this is, again, like a slightly more advanced method. Now you have your conclusion that for all n, it is true. Okay. Step 3 is profit. So this is what you'll actually see when people write research papers, which is basically they'll pretend like they never did step 1. Like they won't show you all the work they did for step 1. And then they're just going to write like, here is my theorem, and here's my very beautiful proof. And they'll never show you all the work for like trying to guess what it might be, like all the other stuff they had to do, right? So that's what it means by profit. This is like the final answer. This is like, here's my theorem, here's my proof. Before you get to that, you usually have to do like a lot of work, a lot of stuff, right? So we're going to practice a little bit more with substitution method. Does everybody kind of follow along like what the method basically is? It's like have a guess that maybe somebody gives you. Try to prove it with induction. If it proves, then like you're done. If you can't prove it, then your guess is wrong. So guess again. You like repeat that loop for a while. Once you have proven it correct, then you like jump to step 3 and you like pretend, you like tell the whole world, like I did no other work. Here's my beautiful theorem and here's my proof, right? Yeah. Yeah, so if you guys actually like ever read research papers and you like see how pretty everything is, like that's after people have like tried many different things for a long time. So another example we can try is a slightly different algorithm where my base case is t of 2 equal to 2. That's the one we're given. And instead of n work, I do 32 n work to merge the solutions. But it's still essentially the same, I would say. So, you know, because it's essentially the same, like not that different, you would use master theorem to get the answer. Alternatively, you would say this kind of really reminds me of another formula that I've seen before. So I think the guess is n log n, or something to do with n log n. Okay. So that's where this guess is coming from. It's just like I looked at this problem, I saw one like it before, so I think it might be this, right? Again, divine inspiration. So you do the same thing. Again, like we just walked through this, but essentially what we do is now we try to prove it. And here what I'm doing is I'm doing it a little bit more generally, where I added this constant in front of the n log n, because I don't actually know, like is it +1, -1? Is it like 3 times n? You know, 3 times n log n, is it 5 times n log n? Like I don't actually know what it is. But if you try to prove it, you'll notice this. You'll notice a couple of things. Okay, so I guess we'll stay here. So this is my guess. Again, my inductive hypothesis is that this must be true for n greater than or equal to 2. Okay. My base case, T of 2 is equal to 2. So this only works. So 2 log 2, this is 1, this is 2. So this only works if C is greater than or equal to 1, right? So I already now have a restriction on what C is supposed to be from my base case. So I'm kind of working through the proof. I'm not proving it yet because I don't know what C is. The actual proof is like you would say C is this, and now I'm going to show you that everything works. Here is like before I know what C is, I walk through the proof, and this tells me, okay, well, C has to be bigger than or equal to 1. That's all I know so far, okay? And then I jump into my inductive step, which is not more complicated, but more stuff. So again, like assume it holds for n less than k. By definition, T of k is equal to this, right? This is by definition, I didn't do anything. This part by the inductive hypothesis, I can replace it with this part, right? Because k divided by 2 is smaller than k. And I assume that for values smaller than k, my guess is right. So I go ahead and replace it. And then if you do some math and simplify it down, you get to this, which is what you want. But now you have the restriction that C has to be bigger than or equal to 32, okay? Because what we're trying to prove, if you remember, is that T of n is less than or equal to something times n log n. This only works if the C is bigger than or equal to 32 from this part here. So what you actually get when you simplify the math is k times C log k plus 32 minus C. If this C is less than 32, then this value is actually smaller than what you're looking for, right? So because it'll be like, 32 minus 0, or like let's say minus 1, then I have a 31 left over. So I cannot say that T of k is less than k C log k, right? Like I can't say it's less than k 1 log k because I'll have a 31 left over. So it must be bigger than 32. Okay, so again, this is a pretty advanced method, but normally this is how you would try to work it out. So now essentially we tried to prove it. That was step 2. And we realized that as we were working through the proof, the only way the proof would work is if we had a value of C bigger than or equal to 32. Okay, so now we profit. Now we go back to our research paper or whatever we're writing, our homework assignment, and we say, all that work that I did, pretend I didn't do it. I just magically knew from the beginning that this needed to be 32 times n log n, okay? And so this is what you would write. This is what you would normally see. Like this is like the final proof. It's everything we just did, except instead of having the C, from the beginning, I start with like 32. And I'm just like, I already knew it was 32. Like I didn't have to do any other work. I just knew it was 32. And the math is the part that like works, like checks out. Because here you get, like I said, you get plus 32 minus 32. So these basically cancel. And then you're left with 32 times k log k, which is what you wanted to prove. If this was not 32, you would not be able to simplify here. So that's, yeah. How are folks feeling about some of this stuff? Thumbs up, thumbs down. Thumbs down. Okay. All right. Yeah, getting the n log n is pretty, yeah, this is pretty confusing. On the homework, you will not be asked to do this, probably not on the final. But for the few of you that maybe followed along, let's say 10% of the class, that is like, this is kind of cool, I like it. This is the stuff that, yeah, I expect very few people to like be able to naturally do this. But if you can do it, then you're worth a lot. So you should focus on this and try to solve these hard problems, okay? See somebody on chat. Okay, so a couple of folks are saying it's confusing. They might have to rewatch after class. That's okay. Again, I won't test you on the substitution method, but I do want to introduce you guys during lecture, especially for like, maybe 10 of you out there that are like more advanced or like are more interested on this side of things to look at this. You will be tested on the master theorem. That is like everyone should be able to do because you do use it in like your job. And again, like we kind of talked about this, like in general, master theorem is not enough, but it'll cover like 95% of the cases. So if you don't know the other 5%, I guess that's when you like phone up your smart friend and you're like, hey, master theorem doesn't work for this. Can you use substitution method to like help me out, right? So what we've learned so far, let's review. Again, so this is like the things you guys should learn from the lecture. A recurrence relation, let me close this, is just the function that is expressed in terms of itself for some value smaller than it. So when I ask you on the homework, here is a code, write me a recurrence relation, you guys should be able to do that. Because the recurrence relation is not solving it, it's just saying, okay, T of n, so the running time of my algorithm for size n is equal to how many subproblems do I have? How much smaller do the subproblems get, right? So it'll be like 2. I have 2 subproblems. Each one gets smaller by 2. So you'd say T of n equals 2 times T of n myself, like T of n divided by 2, because now my problem got smaller, plus how much work do I have to do to bring the problems together, all right? So that is what you really need to know how to do, I would say, for like the real world. So just remember that, recurrence relations. Yeah. You almost only use it for recursive methods. Yeah, because like if you have code that is not recursive, yeah, I'm sure you can write a recurrence relation for it, but it's like it's probably easier to actually just look at the code and be like, it has a for loop that iterates for this, so it's O of n, right? This only helps for like if you have a recursive method where it's a little harder to figure out like what is the running time, because you're like calling yourself, and like you might be calling yourself multiple times or whatever, right? Yeah. Great question. So here's an example, right? So this is what, so going backwards, this is the recurrence relation. What algorithm might give you this recurrence relation? Like, what is the algorithm doing to give you this? Yeah. Yeah, that makes a lot of sense. So it's one of those methods where it's essentially cutting the problem in half and calling itself twice. All right, so you kind of already know like the recursion, what it's doing there. And then this 11n is basically saying like, well, my merging doesn't take me just linear time. I might be like merging like 11 times or whatever. So you might not see this algorithm in real life, but you would think like it's probably being a little bit more expensive than like our merge sort when it tries to merge. Like it might be doing other stuff. Like maybe it like merges once and then like takes the 2 results and like merges them in reverse order. And then I don't know, like something crazy. And then, like I said, this is the most important one. So master method, once you have this recurrence relation, you should immediately be able to jump to the answer. Yeah. Yeah, so I'll say this. So for recurrence relations with algorithms, this is probably a bad example because this 11n doesn't matter. If you remember from the master theorem, what matters is the exponent on the n, not the constant next to it, right? So this is probably a poor example, but so I wouldn't even know how to figure out it's 11 versus 10 because that's like trying to count how many for loops and stuff. So you wouldn't do that. The things that will change are basically like how many subproblems, how much smaller do they get? So they could get smaller by a 4th instead of a 3rd, or they could get smaller by like, you know, a 5th or something, right? And then here, what's going to matter, usually it'll be like, is this n squared, n cubed, right? So the work to bring my solutions together, do I have like a for loop in order to bring them together? Or do I have just merge, which is just like, I guess 1 for loop, do I have 2 for loop, 3 for loop? Like how many for loops do I have? Yeah. So master theorem, please remember that. Substitution method, this one you don't really need to know as well. But if you enjoyed today's lecture, come talk to me in student hours because I think there's a lot of people I've worked with that don't know this method that well either. So it's like you'll be like, it could be like you're different. You're different if you enjoy that. All right. So again, to remind you guys, master theorem. I think I'm going to skip this because I've shown you this slide before, but all it boils down is like once you have the recurrence relation, you just look at the constants, you look at the cases, and then it gives you the answer, right? So now you don't have to draw trees or think about it. You actually just look it up, basically. This is the substitution method that we just covered.
So substitution and master theorem, they won't always end up 5% time.
So substitution will always work. But the hard part with substitution is you have to make a guess. So that's like the part where it's like, how do I even do that? Which the answer is, there is no answer. You just have to like try different things and like
you work so many n log n problems, you can like infer
this is like some constant times n log n. Yeah, for a lot. Or you'll be like, oh, I think this is n squared, or I think this is linear. And we'll actually do another example coming up for that. But yeah, that's the part. I think that's why substitution method is harder, because there is no like, make your formula, look up the numbers, and then look at this formula, and then it tells you what the answer is. It's more like this very first step is actually very difficult for a problem you've never seen before. It's like, I don't know. So like what some people usually do is they'll try n and log n, they'll try n squared, they'll try n cubed, and then, you know, and there's many possible answers, but they'll try a few, maybe one of them works, they get lucky, you know, so it's like a lot of work. So it's actually, so one of the reasons you do also learn the substitution method is that, for example, this is a valid recurrence relation. So can somebody intuitively tell me what this algorithm would be doing if this was the recurrence relation for it? Because we're actually going to see a recurrence relation like this for the next algorithm we learn. Yeah. Yeah. So basically, we are splitting our input into two sections. One is 1/5 of the original size. So maybe like the first 20% of the input. I don't know. The other is 7/10 of the original size. So it's like we're not even splitting like in half anymore. We're like somehow, and we're gonna see an algorithm that does this like on Friday. So like this is not like, and it's actually a very useful algorithm. It's not like you don't ever see this, but it's basically saying like, oh, I'm splitting into different sized halves. One is 1/5, one is 7/10. Where do those numbers come from? You try it out. I call myself on both of those as input now. So that's why we're calling the T again. And then once I have the answers to those sub problems, it takes me about n time to like put them together. So this is an example where master theorem wouldn't work at all, right? Because you have two T's basically that are like different. You can't like, you know, they're not the same. So you can't just say 2 times something, right? It's like they're different. So again, here's like a base case. So again, like I said, the master theorem would not work in this case. And we will see an algorithm that does this next lecture. So like I told you, there are cases where the master theorem just does not work. So this is one where you would have to use substitution. So yeah, what would you guys guess the running time is of this algorithm? Yeah. O of n. Okay, I have an O of n guess. Who else agrees with that? Agreement? Okay, so they think it's linear. They think even though I'm calling myself twice and splitting this up, it's still going to be linear. Okay, I have a guess for n log n. Somebody thinks it's n log n. So I will tell you, like, one way that you might guess this is that a fifth is basically 2/10, and 7/10 is like, so 2/10 plus 7/10 is actually 9/10. So like each call, you're like throwing away part of your array. So it's actually O of n. So like that's something that, but like again, like I don't expect you guys to know this, but this is something that you will like notice as you do more recurrence relations, where it's like, if I'm looking at a strictly smaller part of my array and I'm doing linear work to put it together, okay, then my algorithm is linear. It's probably linear, okay. So I start with an array of size n. And how much of the array in total am I like looking into when I make my two calls? 9/10, right? 9/10, which is less than the total array, right? So one thing that people notice with recurrence relations is if I'm looking at less of the array in total, then it actually ends up being O of n. It ends up being O of whatever this is. If this is n, it'll be n. If it's n squared, it'll be n squared. Because like essentially, the tree ends up being like it's one of those trees that is like skinnier rather than like really bushy. So most of the work's actually done at the top. It'll be n log n when these equal to n. So no matter how you split them up, if this was 3/10 and this was 7/10, because they add up to 1, then you might guess n log n. And then if they add up to more than 1, then you would guess the other case of the master theorem. So anyway, that is a good guess. Whoever guessed O of n. N log n is also a good guess because you're split into 2. You might try both. Another way you can try to figure this out is you can actually just like code it up and like write the function. So this is actually what some people do, which is if you write this function in like Mathematica or Python or whatever, it kind of looks linear. So that's another way to try to guess what it is you like graph it for the first 1,000 values, and then see what the answer is. So now what you would do next is step 2. You would want to prove that it's right. So you would start with your inductive hypothesis. So T of n is less than or equal to some constant times n. So I want to prove that it's big O of n, right? Then I have my base case. So my base case is supposed to hold for all numbers from 1 to 10. T of n is supposed to be equal to 1. Then I have my inductive step. So again, assume that my inductive hypothesis holds. So now k is bigger than 10 because my base case covers all the values less than 10. And I assume it holds up to k. So by definition, T of k is equal to this, right? These are each smaller than k, so I can replace them with the answer I'm guessing. So I can replace them with c times n, right? C times k divided by 5, c times 7k divided by 10, right? Because they're smaller than k. So the whole thing about the inductive hypothesis is like, I don't know if it works for k, but I do know it works for numbers smaller than k, right? So again, if you do some math and like simplify that out, you actually get, if you essentially you're trying to add 7 and then 2/10, 7/10, and then 1k, which is 10/10. We want to show that this holds for n equal to k. Right, see? So we don't know what C is. We're just doing all the work. We don't know what it is. So we leave it in. We work through the proof. Here, this tells us that we have to choose C bigger than or equal to 1, because that's the only way that 1 is going to be less than or equal to C times n. Because when n is 1, this is 1 is equal to C, right? So if C is smaller than 1, this is not. So it must be bigger than or equal to 1. So from that case, we know it's bigger than or equal to 1. And then from this case, at the bottom, you just work it out. So you notice that this is 2/10 plus 7/10. So that gives you 9/10 k, right? And this is 1k, which is 10/10. So in total, it's like 19/10 k. So you can pick anything that's bigger than 19/10 and it works. You can pick 10 and it works, okay? So then you go to step 3, which is just profit. So just finish up your work. So this is exactly what we did, except it's the same thing we just did, except now we're saying like, oh, I knew it was 10 the whole time. I knew the number that was going to work was 10, right? So I'm not keeping the C around. I'm going to pretend I'm really smart. And like, I knew from the beginning, it should have always been 10. And then you notice that you can, this is the part that matters, which is like if you plug in 10 here and 10 here for C, then this is 7 times K. This is 2. So 2 plus 7 is 9, plus 1 is 10. And that is less than or equal to 10, right? If you had picked another number like 5, then this wouldn't work out, right? So that's why you have to pick 10 or bigger, right? And you're done, right? Now you publish this as your proof and you tell somebody, by the way, this recurrence I showed you, the running time is O of n, here's the proof. And you can check my math because everybody agrees on math, right? Again, so substitution method can work when the master theorem method doesn't. So in particular, the master theorem only works when you're splitting your array into equal sized parts. If you're ever splitting it into parts that are not equal, master theorem is not going to work for you. You will have to use substitution. 95% of the time, you split your arrays into equal parts. So yeah. Like we said, for the substitution method, you generate a guess. However you want to do that, you throw your kitchen sink at it. You like throw the baby out with the bathwater. I don't know. You like just pretend you know the answer. Then you try to prove it, and then you profit. Is this even useful? So here's a question, which I have been alluding to this whole lecture. And the answer is yes. So there are many recursive problems where it's not just split it into 2 or split into thirds. Okay. And we're actually going to see one today. I will introduce you to the problem. I'll let you guys think about it over Thursday, and then we will solve it next on Friday. So the problem is called the K-select problem. Okay, so this is actually an algorithm you will need to know. So please pay attention to this part for the last few minutes of the class. I am only introducing you to the problem. I am not giving you the solution. We will do the solution on Friday. We will assume that all elements in the array are distinct. It just helps us if we do that with all the proofs. Okay, so does everybody understand what that means? Okay, cool. So basically the K-select problem is given an array of some numbers. I want to select the kth smallest element. Okay. So let's walk through some examples for what that means. Okay, this is the problem. I'm going to be given an array and a number k. And what I want is I want my algorithm to give me the kth smallest. So this, you can imagine, gets used like if you want to get the top 10 news articles to show somebody, there's an array of news articles and you sort them in some way. Hint, one possible way to solve it. And then you're trying to find the one that is like, you know, the 10th highest, right? But maybe you want to show the top 20 articles. So you want to find the 20th highest, right? So here's a few examples. So select A of 1 is saying the one smallest element. So that's actually 1, this one. It's the smallest, okay, out of this array. Select A of 2 is saying what is the second smallest element? The second smallest element is 3 right here, right? And then a couple more examples. You have 2 more minutes, so we will cover this. You can imagine essentially select A of 1 is the minimum. It's the same as writing a code to pick the minimum value of the array, okay? Select A of n, like the nth smallest, is the same as selecting the maximum value, okay? Selecting A of n divided by 2 is like somebody's asking you, give me the middle value, the median of the array, okay? So the problem with this is actually for these, you guys probably can come up with a linear time algorithm that solves the minimum, right? Just iterate over the array, find the minimum. The interesting thing with this problem is you don't know k up front. Somebody might ask you for different k's, okay? So how would you solve it? So actually, yeah, I think you guys know enough to actually solve this problem. Like, give me a pretty good solution, like right now. Any suggestions? Somebody mentioned sort it first. Okay, I hope that for most of you, that was something you thought of when I introduced this problem, which is I'm trying to find the kth smallest. You might have said, wait, I can just sort the array first. And then I know exactly where the smallest is. It's the beginning. And the second smallest is the second one. So yeah, that's exactly it. You call merge sort on your array, and then you return k-1. The reason it's k-1 is because the problem is defined as like the first smallest is actually the 0th element. So there's like an off by 1 thing. the running time of this algorithm is n log n. So there you go. You guys actually already have a solution that if I ask you this problem in an interview question, this should be like one of the first answers you come up with, right? You're like, oh, I could just sort it and then pick it, all right? Now, but the next question you should naturally ask yourself is, can I do better? All right, so I think next lecture, we will start going to when I can do better. I did have a couple more slides, but here's what I'll tell you. We are hoping to get a linear time algorithm for this general problem of selecting the kth element. Yeah. Yeah. For this code would probably be a little bit more. We'll code it up on Friday. We'll code up this solution because you guys already have merge sort. So we'll just code up this solution to this problem on Friday in class. And then you guys can look at the next slides. Yeah, we'll cover the next slides next time. Thanks for coming, guys. But yeah, that's it. Oh, I guess I always ask, which is like, how is the pace today? Too slow? Just a lot. Okay, a lot of content, so maybe a little too fast. Yeah, it's like yeah. This is probably the hardest proofs that we're gonna do in this class. It should get easy. Like I think the rest of the concepts will be more algorithm intuitive based. Okay. Yeah, and all these slides are on the website, the lecture notes as well. So, and the video I'll post it today. So yeah, what's up?
The cutting part, this